start this recording here. Make sure this is down. All right. Good. So everyone has all the examples here, saving us a bit of writing. So what I decided to do, at first I was pulling examples, but then our examples list was like huge, and I really don't think we'll have time to cover all of them. And so I just stuck with the ones in the textbook. The reason being is because that's the resource that you have, right? And so, and they use a lot of mathy terminology, right? And so I just want to go through and talk it through with you. And I guess it's important. So some textbooks kind of don't use so much math notation, but flipping through your hydrology textbook, for example, you do need to be very comfortable with math notation. And so that's why I'm spending the time here. It's going to be a lot of new terms, potentially, right? But just sit back, relax, enjoy the ride, learn some math, but not in the way you think. Does everyone have a copy of assignment 2, which is due on Thursday? Cool. If you don't, I have the extra copies. And if you want to hand it in early, that's great. That's allowed. That's always allowed. For me, I guess, maybe not for everyone. But I'm confident in my organizational skills that I can keep track of them. Bold statement. All right. Marty. Oh, thank you. So, my skill at assessing how much we can cover in a day was not very good initially, but I think we're just going to get through 1.1 today. And then next day, so on Thursday, I think we'll only be able to get through 1.2 and maybe 1.3. So for test 1, it'll just cover chapter 1 and the background information in the stats section, right? And so there's a lot of steps there. But in terms of the textbook, only chapter 1, okay? And so test 1, oops, I need to connect this, don't I? Test number 1 will only cover, I should put only in quotes, only cover the background information, which was essentially that skills assessment that we did, statistics, so assignment 2, and chapter 1, oops, and chapter 1, right? 1.1 to 1.4, so not all of it, even. Okay, so what I want to do is I want to go through and introduce all the concepts, okay, and then we'll work through the examples, right? Because what I find is when we do a concept, do an example, that's good, right? But when you're looking at these problems on an assignment, for example, they're not lined up like that, right? And so it's important to be able to see something and know where to go in your notes for it. And so I've decided to set it up that way. Give it a go. All right. Section 1.1. Functions and their representation. So, oops, and their representations. So at the heart of all math, we've got functions, right? And so we need to be really comfortable knowing what functions are. So the first concept we need to introduce as we start expanding our mathematical skill set. So we start expanding our mathematical skill set is that of a function. So functions are everywhere. So as soon as you're saying that this result depends on this, you've got a function, right? And so in nearly every physical phenomena, physical phenomenon, we observe that one quantity depends on another. So, for example, your height depends on your age, right? Temperature depends on the day, right? Time of year. So everything kind of depends on something else, and that's a function. So your height depends on age up to a certain point, right? You have to be careful because I think in our minds, we usually think of linear functions, right? Which we saw in the statistics section where you have a straight line and things just keep going and going and going. But functions can actually take many different shapes, right? And so if we're talking about height with age, right, then you've got this upward kind of linear slope and then we kind of teeter off, right? We stop growing. And so your height depends on age, the temperature, and the temperature depends on the date, etc. We use the term function, right, to describe this dependence. Right? Something depends on another thing. So we use the term function to describe this dependence. One quantity on another. So far, I think we're all, yeah, what about it? Formally, though, I'll tell you what a function is. So formally, right, kind of official math speak, we say that given two sets, capital A and capital B, a function from A to B is a process. Oh. It turned one of my letters into a triangle, and I think it's an A. I guess they released this update where if you hold down long enough, it'll just change whatever you drew into a shape. And I think my A's are going to turn into triangles. A function from A to B is a process. You know what? I'm going to, because there's a line break. Is a process by which each element of A is matched with, right? Or if you want, you can say mapped to, or mapped to one and only one element of B. It's a formal definition, so I'll put a little pink square around it or something. So we're talking about sets. Sets are just sets of numbers, right? And so what we can do is we can show this kind of mapping where we have some input in the set A, okay? This box represents just all the numbers in A, whatever they are, right? And then we've got some output. Which is the set B. So what it's saying is that from one individual thing in A, so if we've got a set called capital A, typically we denote the thing inside just an individual thing by a lowercase of the same letter, right? And so we've got A, lowercase a, maps to some output f of A, so f and then in brackets A is the output in B. Okay. So I guess you could put f over top of the little arrow, right? Because f is the actual function. It takes A and returns f of A. So we use f of A to denote a function, of course. In this case, a function of A, right, lowercase a. In general, we read f of x is the most common function notation, but it can be anything inside, right? Whatever is inside the brackets is the input, and then f of whatever, so f of x, f of a is the output. So in general, we read f of x as f of x. Oops. So x is the input, and f of x is the output. So what we said here in the definition, we scroll up a little bit. So given two sets A and B, right, so a set of inputs, a set of outputs, a function from A to B is a process by which each element of A is matched with one and only one element in B. So what that says is that for each input, we can only have one possible output. Otherwise, it's not a function. It happens, right? We can have equations that aren't functions, right? But in order to be a function, we can only give it one input, and it can only give us one output. Okay? So the most important property, of a function is that any input can yield only one output. Only one output. Oops. Shapes again. One output.
So can you have multiple inputs that equal the same output?
You can. Yeah. So what it's going to look like is you've got, let's say, A1, A2, A3, B1, B2, B3, right? This is from the set A, and this is from the set B. Right. A1 might map to B2. A2 might map to B2. That's allowed. Right? B3 might map to B1. But what we can't have, right, is that A3 maps to B1 and B3, right? So that's what we're saying. We can only have one line from an input to an output. Okay? You can have more than one line from an output to an input, right? But here, can't have that one. Okay? Any other questions so far? And we'll look at these by mapping them like this. We'll look at them graphically, right? How do we look at a function and see if it's a function we're given a graph? And we'll look at them just numerically or algebraically. Okay? But first we need to do some housekeeping. So a function, if we have a function, then you might recall the domain and range. Domain's usually fine. People have a hard time with the range, but the domain is just what possible values of x can you take, and range is what values of so a function will have a, which is the set of possible inputs and range, which is the set of possible outputs. Things to look out for when you're finding the domain, especially, is you want to look out for illegal math, right? Because as soon as an input results in illegal math, most common being dividing by 0, can't be done, right? So that's illegal math. Taking the square root of a negative number also shan't be done. Can, but it yields imaginary numbers, which we're not gonna, I mean, we're definitely not getting into imaginary numbers. And so we're gonna stick to, they are actually called the real numbers. So imaginary real numbers. And so you can't take the square root of a negative, right? So when identifying the range, or sorry, the domain, identifying the domain of a function, keep an eye out for inputs that result in illegal math, right? Main ones being dividing by 0, or the square root of a negative number, as these inputs will not be part of your domain. Will not be part of your domain. They didn't introduce it in the section, but I think it's important to talk about just kind of overall set notation. And so some common sets include the real numbers, which we draw a capital R, but with 2 lines. Okay, so this is the set of real numbers. So basically any number that you can think of, right? Continuously, forever and ever, from negative infinity to positive infinity, right? No imaginary numbers, right? Square root of -1, but the set of real numbers. Usually I get sloppy and it looks like that, but I'm trying to be good here. Okay. So the set of real numbers is basically all numbers we know, right? Or we know from negative infinity to positive infinity. I'll also introduce the set of integers. So the set of integers is a z, again with a double bar, capital Z. So this is the set of integers, which if you're talking about just examples, it's whole numbers, right? And so we've got -3 to -2, -1, 0, 1, 2, 3, on. I guess I could talk about, right? I've used round brackets there, not really by chance, because they go to infinity and -infinity, right? Just the whole numbers though. And so we use round brackets when we don't know the end of it, right? And I guess here, or for the set of real numbers, we can do the same thing from -infinity to +infinity. Good. All right. How are we feeling so far? Tickety boo? Nice. All right. Let's do some official definitions then. So we can summarize the properties of domain and range formally. And what we're going to do is we're going to write it out, and then I'll highlight some of the things, so some of the notation that I've used that you'll need to keep track of. Okay. Suppose f is a function from A to B. So far, so good. If lowercase a is in the set of capital A, right? So just establishing that, hey, if we're pulling from all these inputs, okay, so if lowercase a is in the set, so that's a kind of an E, right? Is in the set of A. I guess it's in the set of. We write f of A to denote the unique element B, to denote the unique element of B. Makes a difference. To which, F matches A. we've already talked about this, right? So this point is not new, right? It's just saying, okay, well, if we're given A and then we put it into the function f, right, the output is going to be f of A. That is just really hammering it home. If we view A as the input to f, then f of A is the output from f, is the output from f. That point, right, is old news. Okay? But it's just kind of showing you all these different ways that we can say the same thing. And when you see something like this, you really have to pick it apart and figure out what it's saying. And then you'll be like, oh, well, I already said that earlier, right? And so it's just a matter of introducing you to all these different things. Mostly notation. Here's our new things, or not new. We already talked about the domain and range, but here they are formally. And so the set A is called the domain so all the values in A, that's our domain. Said differently, the domain of a function is the set of inputs to the function. Again, just saying, okay, well, if we're thinking about a graph, right, what values of x can we have? Okay. Or what inputs can we have? So the domain is kind of fine as long as you're keeping an eye out for inputs that yield division by 0, right? Those are not in the domain. Inputs that yield square roots of negative numbers, those are not in the domain, right? And so the domain is kind of fine. The range, we'll say the set, and here we're going to use set notation, curly bracket. The set f of A such that, so a vertical line is such that A is in the set of A, and then end curly bracket. Oh, that's nasty. I'll dissect it after we write this little blurb. Okay. But so the set of f of A such that A is in capital A is called the range of f. It's called the range of f. Said differently, the range of a function is the set of outputs from the function. I'll put I'm not even sure I can. It's too big, this definition. There we go. Whee! There. Let's talk about, so here, we used some notation. We should go over. Right. We've already seen lowercase a is in the set of A, but I'll just summarize it here. A is in the set of A, says that A is in the set of capital A. Curly brackets. My left one's usually pretty good, but somehow my right one always has like a double beak. I don't know, and when I get lazy, I just do this. But try your hand at those curly brackets. They should, if I'm drawing a beautiful one, oh, maybe I said too much. Should look like that, right? And then, oh, here we go. Hey, pretty good. All right, if you're drawing these, ditch those. We don't need to have half a page of a set, a beautiful set. Right, so this is set notation. Set notation. Usually we can list the values if we know them, right, separated by commas, or we can just list the conditions that satisfy this set. Okay? And so we place conditions, because this is usually how sets are defined. So we place conditions inside the brackets or if we know the values, we list them separated by commas. We only list unique values, right? So if you have a recurring value, a recurring output, you only list it once. So we only list unique values. Yeah.
So this kind of goes back to what you were saying about the negatives and everything. But
yeah.
So we have one and a negative one.
Yeah.
Is that considered values?
Those would be unique values, right? -1 and 1 are separate. Yeah, totally. But good. Good, good, good. So the next thing we used was just a vertical line, right? Which we just read as such that, or it can also, you can also read it as given. we'll use the vertical line as given, so I want you to be prepared. Right, so the probability of this happening, given that this has already happened, right, use the vertical line. So what we saw was the set of f of a such that a is in nasty curly bracket, capital A. We read this as the set of f of a such that a, lowercase a, is in the set of capital A. Remember that this was the definition of the range, right? Let's just simplify this a little bit. So this is simply saying that as long as A, so a lowercase a is from capital A, I'll put in brackets the domain of F, f of A will make up the range of F. F of A will make up the range of F. So far, we've really only talked about three things, right? We've talked about a function can only take one input and yield one output. Otherwise, it's not a function, right? That's the first thing we talked about, kind of beat it to death. Then we talked about the domain, right? The domain is all values of input that we can have or we can take. And then we talked about the range, which is just all the possible outputs that we can have. Right? We mathed it up a lot. Right? It's a lot of words for it to be math. This is what math is. That's why, yeah. People had no idea what I was doing in my undergrad. Just writing. Therefore, thus, blah, 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 blah. Anyways. How about some new terminology? Right? We're going to have an independent and a dependent variable. And so we'll say, since f of a, we said that the whole point of having a function is because something depends on another thing, right? And so we need terminology for which is which. Since f of a depends on the value of a, we call f of a the dependent variable. And we call a the independent variable. So just going back to the whole point of a function, right? We've got some independent variable that we use as the input, and then we see what output we get. That's the dependent variable. So we're also going to talk about the minimum and the maximum of a function. Now, I think we all have a pretty good idea of what a minimum and a maximum are, right? And so we'll introduce them formally, and then you'll see that, oh, all this notation, I get it. Okay. And so we will also talk about the minimum and the maximum values of f. This actually refers to the outputs of f. Outputs of f. To find the minimum and the maximum, we actually would need calculus, right? We need to be able to take derivatives, but we don't have that, and we're not going to. So what we'll be doing is just looking at it graphically. So, but we can define them and know what they are. I'll skip this page break here. And so we can say formally, suppose f is a function whose range is a set of real numbers containing the values lowercase m and capital M. Lowercase m is going to denote the minimum, and capital M is going to denote the maximum. So what this is saying, okay, so f is a function where the range, right, the possible outputs contains a minimum and a maximum, right? So we're establishing that, okay, this particular function is going to have a minimum and a maximum. There are functions where there are no minimums and maximums, right? The simplest example would be if you've got a line like this, it keeps going and going and going. So there is no minimum and maximum, right? It just keeps going, going. Straight lines just keep going, 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 going. Right? So there is no minimum and maximum. Okay. So here we're just establishing that, okay, f is a function, and at some point in the outputs, we have a minimum and a maximum. The value, lowercase m, is called the minimum of f if, so many f's in there, of f if m is less than, I'll use f of x here, less than or equal to f of x for all x in the domain of f. We know that, right? We know what the minimum is, but this is how we communicate it mathematically, right? And so we know that if we have a set of outputs, that's f of x, right? Then the minimum value is the smallest of those values. Right? And so here we're saying that, okay, well, here, m is the minimum if it's the smallest of all the outputs, right? So m is less than or equal to f of x. And we'll talk more about inequalities, right? But I used to have a heck of a time with inequalities. I don't know why. You guys have heard the alligator eats the big one, right? I didn't actually find that helpful because it's like, well, which ones? I don't know why I didn't find it helpful actually, but I didn't. So it's very obvious. And then a student of mine was actually like, oh no, you just make an L. And then if it's like this, you read it as m is less than or equal to f of x, right? And so you just make your L. And then if it's not an L, then it's greater than, right? And so it's my duty to pass that on, right? And so you just read it. If it makes an L, then you read it as m is less than or equal to f of x. I guess I'll put that little note here. Less than or equal to, right? With a line underneath, we've got or equal to, which I do kind of expect you to remember some inequalities there, but like I said, we'll come back to them as they pop up. What we'll say here, that is the minimum, oops, the minimum of f is the smallest output from f if it exists. Remember in the beginning we established that yes, this function does in fact have a minimum and a maximum. But like I said, there are cases where there is no minimum or a maximum. Same idea. Have you guys had a fire drill yet? I guess it's fire drill season. I guess we'll, yeah, nice, right? Now I'm on high alert. No, it's only because I heard that beeping. But, oh, beginning of term. They're coming. They're usually done by now, though. But anyways, doesn't matter. They decided not to do them. Yeah. The value capital M, same idea, is called the maximum of f if, by the same logic, f of x is less than or equal to capital M. You could write those in reverse order if you want. M is greater than or equal to f of x. That's fine. All I'm saying here is that all the values of f of x have to be less than or equal to the maximum. for all x in the domain of F. Oops. Just as a little summary, that is, the maximum of F is the largest output from F if it exists. That is the maximum of F is the largest output from F if it exists. Okay. Taken together, right, the minimum and the maximum individually are extreme values, right? Together, just more terminology. Sounds like a coffee. Extrema. Oh, sorry, fancy espresso. Taken together, the values lowercase m and capital M, right? Shorthand for maximum or minimum and maximum, if they exist, are called, the extremas, or extrema, I guess. I think it's maybe the extrema is plural. Extrema. You can say extrema too if you want. Yeah, I feel like it's plural of F. Doesn't really matter. Point being, if you see a question that says find the extrema or the extrema of F, you know to find the minimum and the maximum. I feel like I say extrema, but I know when I learned this stuff, my prof said extrema, and so you can say either. It's probably extrema though. Any questions so far? No. This is not what we signed up for. I know. Don't worry, you have to be here, so you have no choice. Okay, so like we said, we'll talk about what do functions look like, just visualizing them, and then we'll talk about what do they look like algebraically, right? So in kind of math, like strict math, and then we'll look at what do they look like graphically, right? And so we need to talk about and develop some terminology around graphing. Oh, I guess I should put a box around this, my kind of definition box. So big. Yeah. I don't want you to memorize these at all, right? I want you to know what they're saying, and I want you to be comfortable reading that type of notation, right? And so you look at it and you say, oh, okay, well, I can break that down, no worries, right? But don't go around, you know, memorizing these, that's crazy, right? Do you know what a minimum and a maximum are, right? Minimum is the smallest value of outputs. Maximum is the largest value of outputs. That's all you need to remember, right? Together, they're the extrema, or extrema. Okay. So we've got a little page break here, so I'll start here. So to graph functions, we will use the Cartesian coordinate plane, which is basically the XY axes that you know and love. Okay. We will use the Cartesian coordinate plane which is essentially anything that looks like you've got X and a Y axis. You've got the main quadrant, right, where X is positive, Y is positive, but then you've got a X is negative, Y is positive, X is negative, Y is negative, Y is negative, X is positive, right? All your four quadrants. Centered here at 0, 0. Okay. So when we say Cartesian coordinate plane, it's just the plane that we're most familiar with. Nothing 3D here, which is a good thing because I'm not very good at drawing the Z-axis coming out. Terrible. All right. So we will need ordered pairs Hey, what do you know? Here's an ordered pair. All right. An ordered pair, ordered pairs which look like in round brackets X comma Y. Right. So we've got the X coordinate and the Y coordinate. Right. So we will need ordered pairs in order to draw functions on the Cartesian plane. So what do we have? We have given a function f with domain capital A, we can represent f graphically using, so f is equal to the set of ordered pairs A comma f of A such that A is in capital A and set. So here, if we're graphing the function of f, we need ordered pairs, right? And so we've got ordered pairs here. A is our independent value. So those are all our inputs. and then comma, whatever the output is. And then you roll through all your A's that are in the domain. Right? And then you figure out what the output is, and then you graph those points, right? Because now you've got ordered pairs. Yeah. And then you can draw your function. That is, we represent f as a set of ordered pairs A comma f of A or more generally, we could write an ordered pair as the input comma output. They're saying the same thing. As far as graphing goes, right, we graph our independent variable on our x-axis and our dependent variable, right, the output on the y-axis. We graph our independent variable on the x-axis. Our independent variable, I'll just write up above here that's our input on the x-axis. And our dependent variable, which is our output on the y-axis.
Would this just be one point on a graph, or would this be the whole function?
So it would yield just single points, but what we're saying here is that if we wanted to graph f entirely, we would run through all the A's in the domain.
Okay.
Right, and so we would run through all the possible A's that we could have, right? Which might just be like 4 numbers, right? Or it could be the set of real numbers from negative infinity to positive infinity, right? And everything in between. And that's when you get this continuous function. Okay. Which is a nice segue here. And so we've got when we only have limited data or limited domain, so when we only have limited data, and I'll put in brackets limited domain, with gaps between points, we have a discrete function. So when we just have these points, right, and we don't know what's happening in between them, we have a discrete function. To have a continuous function, means that we can give any input value and find the output value. Means that we can give any input value the this a continuous range of the domain. I know I didn't mix them up. It's all about context, right? And so this requires a continuous domain. And of course, there's another caveat, right, for a certain distance, right, or for a certain stretch, but that's good. If we have a graph of a function, that's great, right? Because what we can do to determine if it's a function is we can use the vertical line test. Okay, so the vertical line test says that as long as you can draw a line, a vertical line, right, so an up and down line, and it only touches the graph once, it's a function. Okay? And so given a graph, we can determine if it is a function, if it is a function, with the vertical line test. If we can draw a vertical line through our graph at any point, so if we can draw a vertical line through our graph at any point, and the vertical line only touches the graph once, it is a function. Well, it's a graph of the function, so but you're right, graph or function. For example, we've got our XY here. If we have a line like this, which we'll talk about later, but we said straight lines we can represent by y equals mx plus b. It's a function where y is a function of x because I can draw these vertical lines at any point and I only cross the graph for the function once. Right. Same if you have something like parabola. Oops. This also passes the vertical line test, right? Because I can do vertical lines all across here, and it's only going to cross the graph once. Yeah. What's not a function? If you have something like not a function. Because here, if we draw, well, maybe I didn't draw it. No, it is. Not a function. Well, y is not a function of x, at least. We're going to be talking about the xy plane, right? And so that's where we have x here and y here. And so note that the xy plane refers to the defaults where x is on the horizontal axis and y is on the vertical axis. And y is on the vertical axis. That's just in case you see a problem and it asks you to graph it on the xy plane, right? It is the plane that you're thinking of, right? XY, but just to confirm. I guess we already defined the vertical line test. We'll do the formal definition of the vertical line test, only because it touches on, well, y has to be a function of x then. So the vertical line test, a graph in the xy plane, there it is, represents y as a function of x if and only if, which we usually shorthand to IFF, if and only if no vertical line intersects the graph more than once. More than once. same idea, right? Here, we're saying that, okay, the vertical line test is checking to see if y is a function of x, right? We can do a horizontal line test to see if x is a function of y. Okay. So similarly, we can use the horizontal line test to determine if x is a function of y. Okay. So let's summarize this. So how can we represent a function? We said, well, we can do it. Oh, yeah, question.
Oh, it's kind of going back, but just like broader understanding, like when you do the squiggle, obviously it had 5 seconds or whatever. Is there a way that you can make that appear on a graph mathematically? It's not a function. It's not. I mean, it's probably not within the scope of.
Yeah, you can.
Okay.
You can model it, but we won't.
Okay.
Yeah. So you can, but yeah.
But it's not like
Not for us. Yeah. We're gonna deal with functions.
Yeah.
Mm-hmm. All right. So let's just summarize the ways to represent a function. Suppose f is a function with domain A, then f can be represented verbally, which we'll see in our examples, right? Not a very common way or even useful way to represent a function, but it's good to kind of get in the groove, right? So verbally, I can say, okay, this function takes a value and it multiplies it by 5, and then it subtracts 4 from that, and then we divide that by 3. That's a function, right? So verbally, or using a mapping diagram, which we kind of did generically in the beginning, but we'll see one. As a set of ordered pairs, of the form input comma output, this usually looks like a table, usually given as a table, which you'll see if you have a look at the examples, right? First one, I give you the function just as a table. If f is a function whose domain and range are subsets of real numbers, so if f is a function whose domain and range are subsets of real numbers. And just as a reminder, right, we can shorthand that to a capital R with kind of two backs, I guess. Then F can be represented algebraically as a formula. Oops, algebraically disappeared. As a formula for f of a. And this is probably how you're most familiar with functions, right? If you have been working with functions, then usually we just have f of a is 3x plus 2 minus 3. I don't know. Or we could also represent them graphically. By plotting the points. In the set A, f of a ordered pairs, given that, or such that A is in the set of A, in the xy plane. So many words. All right. Frame this up here. Let's get to those examples. How about? Oh man. There. So I'm going to steal the example from here. Oops. Oh, I guess I should include the top part. Come on. Okay, I'll just do them separately. So here, right, we've represented the function as ordered pairs, right, in a table. So here, we've represented a function as ordered pairs in a table. Oops. In a table. So Skippy records the outdoor temperature every 2 hours starting at 6 a.m. and ending at 6 p.m. and summarizes the table or the data in the table below. And so we've got the time, which is the number of hours after 6 a.m. Right? Feel like if they'd used a 24-hour clock, it would have been fine, but that's all right. That's just my persuasion. So 0 hours after 6 a.m. is, of course, 6 a.m. It was 64 degrees Fahrenheit outside. 2 hours after 6 a.m., it's 8 a.m., right? It was 67 degrees outside, and so on and so forth, right? Part A, explain why the recorded outdoor temperature, right? And so the outdoor temperature is a function of the corresponding time, right? And so here, we're saying that the output is the temperature and the input is the time. Right. Well, each time, right, each input only maps to a singular temperature, right? And that's the rule for a function. It's fine that at 8 hours after 6 a.m. and 10 hours after 6 a.m., we're getting an output of 83. That's fine, right? Each input is going to only one output. Okay. So since each input time only maps to one output, which is the temperature. Oops. Temperature is a function of time. So just applying that main thing that we talked about in the beginning, right? That in order to be a function, each input can only yield one output. Right? A lot of the time, right, we've got functions because it wouldn't make sense to have at the 0 hour mark, so 0 hours after 6 a.m., it wouldn't really make sense to have 64 and 73, for example, right? That's what two outputs would look like. So right away, because we don't know what to do with that, right? Each time can only yield one output. But that's what it would look like. Is time a function of the outdoor temperature? So can we map from the outdoor temperature to time? No, we can't, right? Because of that 83. So a temperature of 83 maps to both 8 and 10, right? And so it can't be a function. No. Since 83 degrees Fahrenheit maps to 8 and 10 hours after 6 a.m. Time is not a function of temperature. So C, use a mapping diagram to represent the function. All right. I'm going to list all my time points. So I've got time here. That's my input. 0, 2, 4, 6, 8, 10, and 12. Maps to the temperature, and I'm just going to scale them from here. 64, 67, 75, 80, 83, 83, and 82. What we should do is we should only list the unique values, right? Because this is our domain. And this is our range. And we should only list unique values. Right. So for that reason, I'm going to cut the 83, but I think that's the only duplicate in here. Right. So I'll just scratch that one and only have 183. Okay. So all of these map across, and I mean, usually what we would do is we would list the temperatures, right? We would list the range from smallest to largest. But it's just going to look nicer if we keep them in this order. And so we've got 0 to 64, 2 to 67, 4 to 75, 6 to 80, and then 8 to 83, but also 10 to 83, 12 to 82. Oh. Pen doesn't want to cooperate anymore. Oh. So that's a mapping diagram to represent a function. Nothing crazy. Let's steal the rest of these. So now we're saying, okay, well, let f be the function that matches the time to the temperature, right? And so whatever mechanism that happens in between, we're not pretending to know what it is, right? But we're just saying, okay, given these values, you know what the function does, right? You only know what it does for input values of 0, 2, 4, 6, 8, 12, or 10, 12, sorry, right? But that's okay. So we can find and interpret things like f of 2, f of 4, f of 2 plus 4, right? And so let's run through these here. And so, oh, hello? I don't know what happened, but yeah. All right, part D. Let's say part D, part I, lots of subsetting here. F of 2 is just saying, okay, if I give you an input of 2, what's the output? The output at 2 hours after 6 a.m. was 67. F of 4, same idea, at 4 hours, so an input of 4, I get an output of 75. F of 2 plus 4, being careful, but it's safe to add them inside the brackets, right? And so we've got f of 2 plus 4 is the same as f of 6, which is 80. Here's where we have to start being careful, right? because what we'll find is that f of 2 plus 4 is not the same as f of 2 plus f of 4. And so f of 2 plus f of 4, well, f of 2 we know is 67, plus f of 4, which is 75, right? Replacing those. 67 plus 75 it's 142. How about something like f of 2 plus 4? Right, so you have to be really careful when you read these. F of 2, we know we can replace with 67, and then plus 4, it's 71. I think that was, yeah. So for I, solve and interpret f of t equals 83. So notice that we use f of t only because we're talking about time is the input. And so we like to use letters that kind of represent what our input is, right? And so f of t is 83. So we're solve and interpret f of t is 83. Okay. We can kind of talk our way through this. We know that the function gives an output of 83 at 8 and 10 hours after 6 a.m., right? And so those are the solutions to f of t equals 83. And so we know the function gives an output of 83 at t equals 8 and t equals 10. So these are the solutions. That kind of is the interpretation as well, right? If we just throw in t equals 8 hours after 6 a.m. and 10 hours after 6 a.m., but I'm not going to do that because we're short on time. Any questions about that? Yeah.
How would you read it more? Is that the most succinct way you'd write it? Or like I wrote like F bracket like 8 comma T 10 bracket, but is that right or wrong? Like, does it imply something mathematically other than what I'm trying to say?
Yeah.
Because you're not like adding.
Well, the briefest way that you could write this and still be accurate would be f of t equals 83 when t equals 8, 10. Yeah. But I can have a look. I mean, probably wasn't that brief, but. Aye. We'll just do this one. State the range of f. The range of f, if we go back, right, we said that the range is all the list of unique temperatures right? And so we can list them like this. I'm actually gonna write them from smallest to largest, which is easy, right? 64, 67, 75, 80, and then 82 gets bumped into between 83. Yeah.
Oh, yeah, can you not just write like the 64 the lowest value, you know, at some point you can edit
The thing is, usually, yes, but for this specific example, this is everything that we know about the function, right? So we don't actually know how it behaves at 1 hour after 6 a.m., right? We can kind of infer how it would behave, right? But this is the function. So usually, yeah, but we're starting small. And so the range we're gonna write is the set, right? 64, 67, 75, 80, 82, and 83. Using that set notation. It seems like I need to whittle down everything even more, even though I feel like I already did, but I know you don't feel that way, but I do. Anyways, we'll get through it somehow. Any questions? No? All right. Just keep thinking about functions until Thursday, I guess. Nope. Class is done. I'm out of here. Oh.